Good afternoon, everyone. Thank you for tuning in today on a busy work day. And we are in the end of the year, December. Thanks a lot for attending the joining the webinar. This webinar is a part of Stay Ahead with Stackroot webinar series, focusing on building resilient systems with event-driven architecture. I'll just take 2 minutes and then we'll be moving right away with the webinar. So let me just to share a context. This webinar has been a part of the Stackroot Transformative team, where the core focus areas for the offerings that we look at is from architect competence development, product management, project and delivery excellence, business analyst, tech leadership, digital versatilist. We normally these interventions are focused on competence development across the technical ladder or even the delivery roles, where primarily we start from an entry level to the senior most and leadership. Recently, this year, we've won around 17 Brandon Hall Awards as a testament to the recognition that we've received for the delivery and the design, unique design and innovative design for our programs across all the areas with various organizations in Fortune 500 and others. And as a part of our initiatives, we have been continuously engaging to ensure to build a strong digital architecture community. As a part of that initiative, we started with a digital architect conclave in 2023, and in the last 2 years, we have seen a year-on-year growth where we've seen at least 120 plus unique delegates, where we see each of these delegates starts from a basic architect level to moving to all the CXO levels across various or enterprises, and this has been consistently growing. As a part of this, we've received a request to continuously engage the community, which is as a part of this initiative, is where we commenced with the Stay Ahead with Stackroot webinar series. Today, we have the webinar on event-driven architecture, which will be primarily facilitated by our speakers, Rahul as well as Anil. I'll take this opportunity to introduce both. Rahul, honestly, is an he has highlighted that he has kind of been more than 2.5 decades into the industry. He is an engineer by education, an architect by profession, and an evangelist by passion. He has, uh, he has been in the industry. We are working on various areas from software architecture to cloud platforms, product engineering, technology. Sorry, hello. Evangelization, and has been working with various organizations from Infosys, Oracle, and now currently is a part of Tredence as the global learning and development lead. Then introducing Anil. Anil has comes with more than 22 plus years experience, where he has been working closely in the areas of storage management to cloud computing to graphics to architectures in various areas. He has been working in various organizations from Dell, Intel to multiple spanning across multiple decades in various organizations. He has been he has more than 7 publications in very reputed articles and holds more than 8 patents and extensively in various technical areas. So I would like to take this opportunity to introduce both the speakers of today, and we would want to take it forward. Over to you, Aaron.
Thank you. Thank you. Um, Dennis, I think I will share my slide.
Yeah.
Okay, so good afternoon and welcome everyone. Yeah, if you can mute
Yeah.
everyone, and towards the end, I think we will allow a Q&A session where you can unmute, please. Yeah. So good afternoon. Welcome everyone to this webinar on building resilient systems with event-driven architecture. So, I mean, the idea here is to, just give an overview of this emerging or, pretty popular architecture called event-driven architecture. And this architecture actually has been in use in various fields, and I think we at I think Stackroot got a lot of requests from people to cover this topic. This will be somewhat at an introductory level. However, towards the end, my colleague Mr. Rahul will give you some practical applications of event driven architecture based on his own experience. So it's a mix of background information as well as some practical real life use cases. All right, so let's begin, right? uh, let's take a second to think about a scenario where we have a medical or sports wearable device, right? So, I mean, you might have seen this kind of devices. Here is a person who, who wants to do an exercise or who wants to exercise. I mean, it could be any one of us, right? And while doing an exercise, he wants to keep a track of how his exercise is going about and whether he or she is going to meet his exercise goals, right? So in order to track that, they use some kind of a watch or some kind of a wearable device. And this watch or wearable device keeps track of various exercise parameters like your heart rate, how many steps you have taken, what was your blood pressure, right? What was your breathing rate during exercise, and so on and so forth. This may actually also keep track of various parameters during your sleep, or you may wear it throughout the day. Right? So I'm sure many of us are familiar with this kind of a device. But what if you're not the user, but rather the architect or a software developer at the back end, for a company which is developing this kind of a device, and you have been asked to develop the software for this, right? And suddenly you start thinking about what are the different kind of data challenges or algorithmic challenges or computing challenges that you face if you want to support this kind of a device, not just for one person, but let's say millions of users all over the world. So think about what all is required to get this device to work or this kind of a program to work. What kind of data you need to capture, what kind of analysis you need to do, and so on and so forth. So if you're an architect trying to support this kind of a device or this kind of a product, uh, the amount of data that gets captured is really massive, and it's all real time because people are moving all over the world doing this kind of exercise, and as the number of users increase, the amount of data that you capture is only going to multiply, right? And people expect some kind of a real-time analysis and alerts. If some parameters go up or down, you want real-time alerts, you want real-time analysis whether you have met your daily goals, weekly goals, how your exercise is going about. And as the field evolves, you will have some kind of backend algorithms, and these algorithms keep evolving, keep learning, right? So certainly it's not a trivial challenge anymore, right? You also want data analytics, secure access to your data, right? Reliable backup, long term storage, and so on. And the scale itself is unpredictable, right? So it all depends on how many new users log in and how many people use it, or suddenly there is a weekend where more people use it, the scale will increase or the load on your system will increase. So this is basically kind of an example of what we call a real-time system or a system which generates data in real time. And if we look around all of us, all around us, real-time systems are there everywhere. And of late, with IoT or Internet of Things being such a big craze, we have added transducers or CCTV devices or this kind of IoT device all over the place. Every device is getting internet enabled or computer enabled or Wi-Fi enabled or Bluetooth enabled. The scale at which data is being captured and stored has really gone up too much in the last few years. So likewise, if you look at weather and weather analysis and weather patterns and trying to analyze weather and trying to give weather alerts, again this is a kind of a real time system where constantly lots of data gets generated at high speed and needs to be analyzed, right? So in sports we have real time systems where I mean, earlier sports used to happen only in one place and it was just a one-way broadcast. But nowadays, people post their comments on social media or sports channels, and these comments or analysis or videos or people's views have exploded. Suddenly, sports and tracking sports has become a real-time system. Social media, so many social media platforms where millions of people keep posting their comments, photos, and all that. This is another real-time system. So likewise, we have real-time systems in the scientific arena, in the financial arena, stock market trading, for instance, or banks, or all kinds of financial transactions happening, credit card transactions. These are all examples of real-time systems where the backend software or backend system has to handle a large amount of data which is coming streaming at high speed. It needs to be processed. There can be similar systems in manufacturing, transportation, and traffic, for instance, or traffic analysis, or how we want to get real-time traffic data, right? So these are all real-time systems, and real-time systems are there everywhere. And things which were not real-time in the past have suddenly started becoming real-time. If you look at e-commerce, for instance, in the past, people used to buy something and it used to come in 2 days or 3 days. Suddenly, people have started talking about 15-minute delivery and things like that. So, what was not real time in the past has become real time now, right? Or even if it is not, someone can figure out a way to do something in real time just to get some competitive advantage. So, the net result is architects or system designers have been asked to process vast amounts of data in real time, and that's a challenge, right? And so let's look at what kind of challenges we have in real time systems, and these are all really related to data challenges. So everything relates to data challenges in real time systems. So it's all about streaming data which comes at high speed, which comes with a large size, and it's somewhat unpredictable, right? So what do I mean by streaming data? A stream is a continuous flow of data, right? So in all these real-time systems, like the medical device I talked about, or sports, or weather, or social media, a continuous stream of data keeps coming in, and we need to store it, we need to analyze it, and we need to react to it, right? And all this capturing of data, storing of data, and analysis, all of it should happen in parallel, right? So it can't be in sequence. I capture the data, I store it, I analyze it, I report on it, then I take the next data. I mean, that is not possible in the real time scenario. So we need dedicated systems for capturing data, dedicated systems for storing data, and dedicated systems for analyzing data, all happening in parallel, right? So that's the challenge of a real time system where people's expectations on the reliability are very high. So if you look at all of these systems, for example, social media or sports or medical devices, people expect everything to be reliable. They do not want you. They cannot accept, some samples got missed, or some data got missed, or some things were just dropped, or we could not cope up with the speed, and so we slowed down things. No, with a real time system, things are happening in real time. Your system cannot afford to drop anything, right? But at the same time, if you look at, I mean, most of these things are implemented in cloud, but cloud is not as reliable. I mean, there can be occasional failures. If you look at any cloud platform, they do not guarantee you like 24 by 7 availability. If you look at AWS or Azure or any of these platforms and look at their fine print, they say we'll have 99.9% availability, right? 99.9% means 0.1% failure. So out of, if you apply that to a real time system, out of 1,000 data points, one can be missed. Now that one data point could be the crucial one, right? Or out of 1,000 comments by users, one could be missed. So the the infrastructure is not as reliable as what our end users expect us to be. And that is where the challenge comes into picture. So meeting all these challenges of real-time systems, right, is what event-driven architecture is one of the solutions. I won't say that is the only solution, but really event-driven architecture is one of the premier solutions. Short form, we call it EDA. So EDA is one of the well-known or preferred solutions to handle data challenges in real-time systems. So really, if you have a real-time system or a near real-time system and you want to analyze it and you want to have a system which can capture, store, and analyze all the data simultaneously with high reliability, and in spite of underlying system prone to occasional failures, right? Then probably you should consider an event-driven architecture as the preferred solution for it. So why is that so? I mean, why is it? I mean, how is it that an event-driven architecture is able to solve many of these challenges? So that's what we are going to look at. So the context is high-speed streaming data in a near real-time system with high expectations of reliability, right? And how does event-driven architecture actually allow you to meet that challenge? So what is event-driven architecture? So as the name suggests, it is driven by events, right? So it's a distributed architecture, right? So distributed in the sense you'll have multiple servers or multiple machines or multiple components working in parallel, right? Which is good because we want your data capture, storage, and analysis in parallel. So we already know that some amount of parallelism was required, and this architecture is already distributed where subsystems communicate via events, right? So as opposed to or as different from a monolithic architecture, and monolithic architecture is a single system where everything is compiled into a single binary and runs, right? I mean, those were the traditional architectures. Nowadays in the cloud era, very rarely you'll see monolithic architecture in the modern systems. But so this is distributed, it is not monolithic. And as opposed to an API based or API centric architecture. So a distributed architecture could be API centric in the sense you have multiple micro services communicate with each other through APIs, REST API or GraphQL API or any kind of API, right? So that's a more traditional architecture. Even when people go for distributed systems or microservice based architecture, we say, it's good to have APIs, microservices communicate via APIs. But this is slightly different. So our event-driven architecture, even though it is distributed, it is different from other distributed architecture, which are more API centric. And we'll look at it, how it is different. So pictorially, it looks somewhat like this, right? On the left-hand side, I have set of producers, right? And producers are components or systems which publish events, and events could be some occurrences in the real world, real life events, right? For example, weather events or sports events or social media feeds, or, you know, in the example that I gave you about a medical device which is capturing your steps or heart rate or, breathing rate, etc. Each each such sample or each such, captured data can become an event. Or in an IoT kind of a system, you have sensors distributed all over the city or all over the factory. Each value sensed by the sensor can become an event, right? And so these producers publish all those events into some kind of an event stream. So the event stream is central to the event driven architecture, right? So event stream, as the name suggests, is a stream of events. So publishers or producers simply publish these events, right? And then there are other set of actors or other set of components which act on these events. These are called consumers. So as you can see, it's a left-hand side publishing event, right-hand side acting on events. Central to this whole thing is an event stream, right? And it's a distributed and somewhat decoupled kind of an architecture in the sense. Now you can see that producer is not invoking an API on the consumer, right? Or the consumers are not invoking APIs with each other. So none of these, components expose any kind of an API, right? And that is where there's the biggest difference between event-driven architecture and traditional distributed architecture. That these are distributed and decoupled components, but they do not communicate via events, right? So that, in a nutshell, is a event-based architecture or event-driven architecture, right? So basically, you can think of this as asynchronous communication, right? So we know that there are two styles of communication in any distributed architecture: synchronous or asynchronous. Synchronous is easy to implement, easy to debug, but can be slow. Asynchronous is difficult to implement, more complex, but asynchronous helps us in achieving speed, right? Because in asynchronous communication, one party is not waiting on the response from the other party. So here the producer is not waiting for a response from the consumer. Producer keeps, producing events and publishing in the stream. It's not waiting for consumers to finish their work. Consumers, whenever they get time, they pick up events and they act on events. So it's a asynchronous communication style. Okay. So let's dig a bit deeper into this, right? Try to understand what different types of events are we talking about, right? I gave you an example of events of the type, in an exercise scenario, but you could have an IT infrastructure level events. IT infrastructure is, your data center, right? So in a data center, you could have data center level events. For example, some logs getting generated, or some users getting logged in, or a packet entered, a network packet entered, or a storage device became full, or a file was written into a disk, right? So network storage or compute level events, memory getting allocated. So these are all IT infrastructure events. You could think of a system where a data center management software which wants to analyze the stream of events at IT infrastructure level. Likewise, there could be events at a slightly higher level. These are data events. So IoT events or something at the, like, let's say you captured some weather data, right? Or medical data, right? So these are all data events. Some external event that got captured, these are called data events. There can be events at an application levels, at a slightly higher level. Like, let's say an application has multiple modules or multiple subsystems. So an application finished a task, right? Let's say an application came up, right? Or application went down, or it created new threads, or a new process got created, or a particular algorithm completed, or particular algorithm completed a checkpoint. So applications can log such events, right? And at a even higher level, you could have business events, or let's say you have an e-commerce business, then an order getting generated, or order getting shipped, or a user's wallet getting empty, or some money getting added into the wallet, or, let's say if you have a food ordering platform, then the new order getting generated to a restaurant. These are all at a business level, right? So events could be at the lowest level, which would be infrastructure, a middle level, which is a data, slightly higher level applications, like even higher level, which are business, right? So different kind of events get generated, and our event driven architecture is actually able to handle events at different levels using different mechanisms. You can actually segregate these events, right? So any event driven architecture is not going to use a single stream where all types of events go into single stream, it'll be difficult for the consumers to figure out which events to work on. So event driven architecture always tries to segregate them or categorize them right at the production level, right? So if you dig a little bit deeper into an event driven architecture and look at the event streams, I'm kind of expanded the middle box, which is event stream. So this is how the event streams look like, right? So on the left side, we have producers which are feeding events, but they are not feeding all events into a single stream. Rather, we have split this event stream box into multiple topics, right? Now, what is a topic? A topic could be anything, depending on, is it an infrastructure event or business event or data event or application event, or within, let's say I have multiple data events. So to carry forward the example of a medical device, I could create a topic for heart rate, right? Another topic for exercise steps, another topic for sleep, another topic for blood pressure, and you know things of that sort. So producers, as they get events, they feed them into different topics, right? And each topic is a stream, right, of related events, right? So events flows from left to right like a river stream, right? And producers keep feeding these events from the left. It is a kind of a FIFO kind of a model, right? First in, first out. So event go from left to right. Producers feed event from the left. Consumers pick them from the right, right? If you look at the consumers, right, different consumers subscribe to different topics. So I might have one consumer only dedicated to one topic. I might have another consumer which is actually analyzing two different topics, another consumer analyzing two different topics. You could have the same topic fed to multiple consumers. So it's quite possible that a particular event stream is analyzed by two consumers simply because one consumer is looking at each event to see if there is an anomaly. Another consumer may be analyzing these events at a statistical level to see, analyze 1,000 events to find out what is the rate of, say whether events getting generated or what's the average, or, some statistical analysis. So basically, event streams and event-driven architecture is quite flexible. It's up to the architect to figure out how to create these topics, how to split events into topics, how to come up with consumers who can, process these topics. Uh, Really speaking, the producers and consumers are far away from each other. Producers don't care whether event that he has put in the stream is actually analyzed by consumer or not, and there is no direct correlation, right, between the two. You could even have new consumers getting added into the system without bothering or changing the producer. So in a way, it's very inherent. You could have one team of engineers working on the producer side, one team of engineers working on the consumer side, right? And so a distributed development team is able to implement an event-driven architecture very well. To even give more scale to it, you can split these all these event streams into multiple partitions. So partitions may be implemented on multiple servers, right? So that even if one server goes down, another server is up. So in a way, you will never have a situation where real time data is getting generated but it cannot be fed because our event stream went down. So event stream, because it's so central to this entire architecture, must be architected with multiple partitions, multiple topics, and a large enough size so that it can capture all these events, right? And consumers are written such that consumers may actually ignore events or may look at events, right? It's quite possible that events stay in this event stream forever. So if a consumer crashes, it can restart and come back to where it left And even if a lot more events have been generated in between, it doesn't matter to it because the consumer can reread the entire event stream. So in that sense, this architecture, the way it is designed, is very, very robust and very, very reliable, right? And because producers and consumers and event stream all work in parallel, this architecture gives you a lot of speed, flexibility, and the capability of handling multiple things simultaneous, right? So how do events work, right? Let's get into a little bit more detail, right? So as far as producers are concerned, producers are not aware of consumers. So they just create an event. Event for them is just a piece of information. For example, a packet has arrived or an order was placed, a user is logged in. They are just reporting it to the world that so and so event has happened. They really don't care how or whether an event is processed or not processed. They just keep doing their job, right? They are also protected from problems on the consumer side. Remember, the real time nature of stream is such that they really don't have time to look at consumers to see hey, whether consumers are really analyzing my events or not. It's not their job. Their job is to just pick up information from the real world, from the external world, IoT or social media or weather or whatever may be the case, capture that event, capture it in their own local database and push it into the event stream and they're done and they just take the next job, right? Stream can accumulate events even when consumers are falling behind because the stream will have enough capacity to buffer events even when consumers are falling behind. Maybe the consumers can catch up, right? So basically there's a lot of loose coupling between producers and consumers. So this is where I want to distinguish between event driven architecture and API based architecture. An API based architecture will stall if the consumers are unable to respond. Imagine a producer makes an API call to a consumer, right? Now, even if we add, a lot of threads on the consumer side or create a lot of connection pools and things of that sort to allow, consumers to process APIs, still there is a limit beyond which, if the underlying API doesn't process, things will stall. Whereas in event driven architecture, typically things do not stall. So that's the basic difference between event driven architecture and API based architecture, specifically with regard to how it handles real time events. Okay. Now, on the consumer side, basically they are also decoupled from producers. They can choose to process an event or ignore an event. They can just look at event but not process it, right? Also, single event can be consumed by multiple consumers, right? A consumer can also become a producer. So consumer can process an event, find an anomaly, and add another event into a different event topic, right? So it becomes very, very flexible in the sense producer generates an event, it's analyzed by consumer, that consumer generates another event, puts it back into the queue, that is in turn picked up by a third consumer, and like that these chain of producers, consumers, further consumers, you can create a very complex and very powerful architecture. So architecture is very flexible and very powerful. The concept itself is very powerful even though it looks very simple at the outset, right? Consumers can be added dynamically, so that gives a lot of flexibility in the sense as your algorithm evolves or as your understanding of your business domain evolves, you can keep evolving on the consumer side. But producers are typically simple, but at a very high speed, right? So producers can do their job, consumers can keep evolving over a period of time as your business grows. So that's how an event driven architecture grows or is able to evolve over a period of time, right? Now, few benefits of this event driven architecture. First of all, it handles streaming data at high speed. I mean, this is the first primary benefit. As we talked about how more and more things are becoming real time and the demands for real time analysis are growing, this is one architecture which is designed to handle streaming data at high speed. That's a fundamental benefit of event driven architecture. It is also highly scalable, elastic, and distributed. Scalable because you can add more processors, more consumers, more topics, right? There is no limit technically to how many consumers you can add. It's highly distributed, right? So you can producers, consumers can be deployed on different servers, on different sites, on different clouds, or different containers, right? So highly distributed, highly scalable, highly elastic. Consumers can be added dynamically, as I said, so it becomes flexible, right? Fundamentally, events are never lost, and that is where we come to that reliability aspect of it. That people expect that these events, maybe they are important events, right, in the event of the life of that person or life of that subject. We don't want them to be lost, and provided we design the central part, the event stream properly, our events are never lost, right? So fundamentally, the one benefit is performance, one on scalability, one on flexibility, and one on reliability. So these are all the major benefits of event driven architecture. So having given you a kind of an overview of what event driven architecture is all about, let's talk a little bit about what kind of tool sets or what kind of software, what kind of packages, or which are the important tool sets which we can use to implement this architecture. So coming to open source, there are two very important tool sets. One is RabbitMQ, another is called Apache Kafka. So I mean, both are open source, so both are popular and both have been used for event-driven architectures. There are certain pro and cons. Among them, I think Apache Kafka is one of the most popular ones and most common ones. And because it is open source, it's continuously being updated, and a large number of people are using it. It's You will hear this name very often whenever you'll say I am using a Kafka cluster. So anytime someone says I am using Kafka, you can understand that it's a event-driven architecture, because Kafka is basically meant for capturing the streams. So the central part, event streams, is actually implemented by Apache Kafka. Of course, you need to write your producers and consumers uh, in Apache Kafka, which could be written in any programming language per se. But the central part, which is the most crucial piece of driven architecture, can be implemented using Apache Kafka. Likewise, you can use RabbitMQ as well. So RabbitMQ is a messaging platform. Uh, uh, it can also be used for creating these kind of event queues or event streams. So sometimes event streams are called event queues. Right? So these are the two important tool sets. Likewise, if you go to AWS, there is AWS product called Event Bridge and SNS. So both Event Bridge and SNS has been used within AWS for creating event-driven architecture. Likewise, Microsoft Azure has Azure Service Bus, Event Grid, and Event Hub. So these are some of the tool sets for implementing event-driven architecture. Now, the thing I want to say is, uh, unless you are sure that your product is going to be purely on AWS or purely on Azure, then it makes sense for you to go for open source tools, right? RabbitMQ or Apache Kafka, because these can be used both on AWS, on Azure, or on your own private cloud, or on Kubernetes, or anywhere you want to use. If you implement your event-driven architecture using any of these, then it becomes more kind of portable across architectures. You're not very much tied to the cloud platform. So to that extent, and also you save cost in terms of licensing cost and all that. So to that extent, it's always better to use open source tools rather than rather than any of these AWS, right? So it saves you license cost, is portable and all that, right? Uh, about Apache Kafka itself, it is open source, as I said. It is one of the most popular tool sets for event-driven architecture. It's highly scalable and it's widely adopted. So, if you are in dilemma at any point of time, which one should I use? Probably you must consider Apache Kafka as one of your first choices, right? And you will find lots of expertise, lot of engineers available, lots of you know reference architectures, some ready-made code, things of that sort. So to that extent, Apache Kafka is one of the most popular tool sets for event-driven architecture. Now, given that we are kind of constrained for time, I am not going to go into too much of detail about what is Apache Kafka, how it is implemented, how it works. But towards the end, I think we will go to some useful references. So you'll find plenty of, we have given some pointers and useful references on both Apache Kafka as well as some of the tool sets on AWS and Azure. So you can refer to them. Okay. So now the question is, this is all fine. EDA is a great tool, but great architecture. When should I use it? Or what are does it have some drawbacks and things like that, right? So question is when to use it and when not to use it, right? If you have a large distributed solution, or if you have a problem which requires a larger distributed solution because of the scale, right? Or if the amount of data that you're going to process or handle is unpredictable, in the sense you don't know, let's say initially your solution has only 1,000 users, the load is less, but you expect the users to multiply to millions, so it's unpredictable, or the kind of demand you face is unpredictable. If you have scalability requirements, in the sense your solution should scale to large number of users or large number of platforms with minimal latency, or if you have some kind of real-time event processing requirement, or if you have a team which is distributed and so you want a decoupled implementation. So if any of these conditions are met, then I think you should consider event-driven architecture, right? Uh, so, I mean, at the same time, if none of these conditions are met, or only one or two of these conditions are met, then maybe event-driven architecture and the complexity of it is not justified, right? So just say if you have scalability requirements, right, but it's not a real-time or distributed implementation, load is not unpredictable, then maybe you don't want so much of complexity, because all said and done, event-driven architecture introduces some kind of complexity because of its asynchronous communication nature, right? So whether you want to pay the price for it is something you need to debate. And if you want to justify using EDA, then at least three or four of these conditions should be met before you can consider EDA. If you think these are met and you want to use, then how do you use it, right? So first of all, you should choose your tool set very, very carefully, because the choice of tool set will decide how reliable or how scalable your solution is. So choose your tool set very, very carefully. As I mentioned earlier, Apache Kafka is a very safe choice. So but you may want to go for Azure or AWS specific toolset, or let's say you're on Google Cloud or some other cloud, and that cloud has a streaming data streaming solution. You can go for it, uh, because maybe you can boot up your system faster, right? So choose your tool set, number one. Number two, you need to make certain design decisions in terms of how do you design your events and things like that. We'll go into that detail in the next slide. So choose a tool set, make some crucial design decisions, and then finally build some kind of a redundancy, because always for event driven architecture, because of unpredictable load and real time event processing, redundancy is a must. Maybe you can use multiple instances of each consumer, right? So consumers, you can have as many consumers as you want. So build some kind of redundancy, especially on the consumer side. Typically, the producers are easy to write, and producers are simple, but because all that they are doing is taking events from an external world and feeding it into the event stream. So writing producers is easy, writing consumers is more complex, and that is where more redundancy needs to be built in. All right. So basically, with this, I come to the initial phase, or kind of overview of this. Right. We are now getting into a little bit of advanced, slightly deeper into the technology kind of section. Maybe just bear with me if I go into too deep into this and you're not really keen on it. But just a few more slides on a little bit more detail. But whatever I've covered so far was the overview of event driven architecture, right? But as I said, if you want to implement, then once you choose the tool set, some more design decisions have to be made, right? So what kind of key design decisions architects have to make, right? The first key decision is, when I'm feeding events into this event stream, how much information should I include with the event, right? Let's say there is an event which says, a user has logged in, right? Do I give all the information about the user? What's the username, right? And what are the roles that person has, and how many attempts for login were made, and things of that sort, so that my consumer can act on it? Or do I just give some kind of a user ID, right? And that's it. And the consumer, whenever he or she, that consumer module process the event, it can retrieve whatever information they need from a common database. So the second approach makes your event stream smaller, because you're just, each event is just an ID, just one integer, right? Whereas the first approach gives it enough information so that the consumer doesn't have to fetch information from a common database. So first approach is faster from a consumption point of view, but takes up too much of space in the event stream. The second option is slower for the consumer, but takes up less space in the event stream. So it's one of the key design decisions to be made, event driven architecture. How much information you keep. The first approach also has the problem that sometimes you put information in event stream, but then after, by the time the consumer gets to process that event, maybe 5 or 10 minutes are over, and during that time that information has become stale because some more changes have happened, right? So there are some trade-offs between these two approaches, right? And likewise, another key design decision to be made is, when you put events in the queue, whether these events persist or they get removed every time they are read by the consumer. So the first approach makes sure that events are never lost, but then events may remain in the queue for a longer time, so your queue size will go up. The second option makes sure that queue size doesn't bloat too much. But if an event is removed by the consumer, and while processing the event, that consumer process crashes, then that event can be dropped, right? They call it, event got dropped or missed or lost, right? Like a packet got dropped, right? So that kind of thing can happen if you follow the second step. Another design decision to be made, right? Uh, so how to ensure that events are not lost? I mean, this is a really involved topic. We said one of the advantages of event-driven architecture is that events are never lost, and that gives us the reliability. But it's not a given. It doesn't automatically happen. You as an architect need to put in some effort to make sure that events are never lost. Let's say a consumer is processing an event, you can still keep it event in the queue, and only when the consumer gives a definitive indication that the event has been fully processed, then you can remove from the queue. So there are approaches by which you can make sure that events are never lost, right? Another big design decision to be made in event driven architecture is how to ensure that same event is not processed multiple times. Now, this is another risk that maybe one consumer process an event and another consumer process the same event, and when the same event is processed twice, it may cause some kind of a side effect, right? So to avoid side effects, you may have to implement idempotency kind of mechanism, right? Idempotency is to involve the topic. I don't want to go into it, but basically it's a way of ensuring that uh, even if same event happens twice, it doesn't cause any side effect, right? So these are some of the important design decisions architects have to make if they have to implement event driven architecture, right? So it's not always hunky dory. There are times when event driven architecture can go wrong, right? And it's good to be aware of what the pitfalls are in this approach, where it can go wrong or where it can cause you trouble, right? So just to give an example, sometimes your event queue can get filled up, right? It's a FIFO, and if the capacity is full, and if there aren't enough consumers or consumers are not fast enough, your queue can get full, and then you know that can put you in trouble, right? Or sometimes your event data can go stale. So for example, you put some event in the database, but some changes happened, right? So whatever you have put in the event queue can become stale, and then you're processing stale piece of information. Sometimes the event stream is the most critical part of this architecture. It can become a single point of failure if it is not properly designed or properly scaled, or it's not big enough or large enough to handle your load. So that's where event driven architecture can go wrong, right? Sometimes, events when they are partially processed and then the consumer dies or hangs, right? That event can be lost. Sometimes it so happens that even though events are coming in order and you may have a series of consumers processing events, because of some problem, events may not be processed in order, and that can cause some kind of reliability issues in your architecture, right? Sometimes, as I mentioned earlier, same event can be processed twice. Okay. The biggest issue can go wrong is when EDA is not the right architecture for your problem. So we talked about what are the use cases where EDA is the right architecture. Choose the architecture carefully. If this is not the right architecture, then there's no point in going for it just because it has so many positives or it's so popular, right? So don't go for it just because it is popular, right? Make sure it is the right architecture for your problem. Let's look into, there are three things we looked at, right? Scalability, performance, and reliability, right? So these are the three biggest advantage of event-driven architecture. How do you ensure scalability? Scalability is ensured first of all by, handling your queue length properly, right? So as your load increases, your queue length starts getting bigger, right? That is a signal that too much data is coming, your consumers are falling behind. That is where you add more consumers, and that is how you ensure scalability. So you can use, scalability features of your cloud, right? So for example, horizontal scalability features or vertical scalability features. Keep monitoring the queue length, and based on the queue length, you can, choose how to use it. There is something called as auto scaling mechanism. So you can choose auto scaling mechanism here. On the other hand, if queue length is too small, then maybe that's a signal that you have too many consumer instances. You can reduce them to save some cost, right? Also, as I said, your queue is the most critical element, so that has to be scaled properly. So depending on the format, your queue size will, go up or down. Similarly, the number of connections you have in the queue depend on how many producer and consumer instances you have. So architecting the event queue properly will ensure you scalability of your solution. To get resiliency or to make sure things are not lost or to make sure events are never lost, if a consumer is unable to process an event, you should put it back into the queue so that someone else can pick up, right? That is one resiliency feature. You can also log events for traceability, right? So it improves resiliency. You can also monitor critical metrics. For example, what is your average queue length? What is your peak queue length, right? The moment your queue length goes beyond a certain point, you can raise an alarm to so that admins can look into the solution. What is the average time taken to process an event? What is the worst time taken? Put some threshold and alarms here. So these are some of the techniques by which you can ensure resiliency. Okay. Likewise, to ensure performance, right? First of all, the asynchronous nature of communication aids in better performance, right? So by its very nature, EDA is asynchronous and gives you good performance. But you know, event queue is the most critical element and that needs to be sized appropriately. It should not become a single point of failure. So as long as you size your event queue properly, you will ensure that performance is met. All right. Now you can use microservices. So we mentioned microservices. Microservice based architecture can go with EDA, right? So EDA fits well with microservice based architecture because your producers and consumers each can be a separate microservice. Microservice can be developed, deployed, and scaled independently. So same thing with EDA. Your producers and consumers can be developed, deployed, and scaled independently. So each microservice can have its own database. So some can be stateless microservice. So typically your consumers can be stateless. Also microservices do not share any data. So even in the EDA architecture, producers and consumers do not share any data as long as enough information is provided with each event. Then microservice architecture can be used to implement event-driven architecture. Let's look at a couple of example case studies. And I think in the second part of the session, Mr. Rahul will talk about some real life examples. But here I have taken a couple of case studies. There was a stock trading and data analytics software, right? So this software used to look at stock trading data. It used to, and this was for the US market. It looked at all the stock values, right? How much volume of trading happened, how many options were traded, what kind of social media feeds were there on these stocks, what kind of news reports came, press release came, industry and market sentiment on that stock. And based on that, it used to give some kind of trading tips to brokers or end users, right? So this was a very good software. It implemented, it was implemented in an API based microservice model, but the architecture, because of this data volume became unpredictable as they added more stocks to it. The data volume became more and more. The algorithms were evolving, and their API based architecture wasn't very flexible. Their backend could not cope up with the load. It couldn't scale beyond a few hundred stocks. So basically, this is where they found both their architecture point of view and from a scalability point of view, they were not able to meet this requirement. Finally, they went for a complete re-architecture based on event-driven architecture, and that actually came to the rescue and it could handle all these challenges. So this is a real example of how a streaming and high-speed, near real-time kind of an application benefited from using event-driven architecture. Likewise, we had an airline reservation software, right? It had input streams in the form of reservation and queries coming from passengers, cancellations, right? And airfare changes coming from airlines. So, a lot of streaming data coming in, right? They had a monolithic architecture for reservations. It wasn't able to really meet the load because of the dynamic nature of inputs. Sometimes some stale data was shown to users, sometimes the latency was very high, sometimes they failed transactions. In general, their architecture could not scale, right? They also adopted an event-driven architecture and they were able to basically meet the requirements of this near real-time streaming. So basically, these are a couple of examples of how real-life systems are able to benefit because of event-driven architecture. Okay. So basically, to summarize, right, event-driven architecture is inherently suited for distributed solutions for any type of real, or near real-time streaming data. It uses asynchronous communication style, and because of that, it aids in the resiliency, scalability, and high performance. And one of the popular implementation choice is Apache Kafka, but there are others as well. Right? So I think that kind of brings us to the end of the first part of our presentation. I would now like to hand it over to Mr. Rahul. I think Mr. Rahul will talk about some of the practical use cases of event-driven architecture. And I think towards the end, then we'll have a couple about 5-10 minutes where both of us will take question and answers. Right? And also towards the end of the presentation, we'll talk about some useful links of external resources for this topic. Okay.
Thank you, Mr. Degwekar. That was really insightful.
Thanks.
So I would share my screen now. Let me know once you see my screen. Hope all of you can see my screen.
Yeah.
Yes.
Perfect. Perfect. So I would like to continue from where Mr. Degwekar stopped, right? I think he talked about event-driven architectures and he primarily talked about Kafka, the implementation details, etc. But I would like to just continue with some more elements of an event-driven architecture. And I would like to do that primarily because those are the elements which I found useful in my practical implementations of EDAs, right? So let me move on to the next slide. So I'm going to talk about certain elements of an EDA, right? So the first element that I would want to talk about is event sourcing. And you might have heard this term, but for those who haven't heard this, what's event sourcing? It's about maintaining the sequence of events such that we can build the state of an application at any point in time, right? So that's event sourcing. Now, what it means is, as and when things happen, right, you maintain those in the right sequence so that if need be, you'll be able to build the current state of the application again, right? Let's take an example. Very simple example, Microsoft Teams, right? Each one of us uses Microsoft Teams and there are so many meeting invites on our calendars, right? So every meeting invite or every appointment basically, has a current state. It's like, when is this appointment? When is this meeting? Who has scheduled this meeting? What time? Who are the attendees? Right? Whether this meeting invite has been forwarded to someone or whether it is cancelled or whether it is a recurring meeting, etc. Right? So this appointment or this meeting invite, right, as and when it is modified, any change to the meeting invite, meaning we change the date, we change the time, right? We add more, participants to this meeting, right? All of that can be considered as an event. And we source each and every event and save that event such that if required, we can build that state again, right? At any point in time, if you were to tell that, look, this is how this meeting was created and how it has changed over a period of time, right? We should be able to do that. And that's the pattern, that's event sourcing. And I'll talk about more practical examples when I move on to the next slide, right? So that's one pattern about sourcing events. The second thing is event streaming, right? So event streaming basically is all about, continuous flow of events. And these events are unbounded in nature, right? So no one knows about, at what rate these events are going to come through and until when, right? It's absolutely an unbounded flow of events that are captured, processed, and consumed in real time, right? So for example, example which all of us can relate to is like detect and respond fraudulent activities by analyzing patterns in transaction data in real time, right? So the moment you do an unusual spend on your credit card, right, immediately you get a call, okay, just to verify whether it's a fraudulent activity or whether it is a genuine activity that you have done, right? Now, this is possible because of event streaming. So basically, it's an unbounded stream of credit card transactions, which is basically going into the system, right? And in response to each and every transaction which is flagged as potential fraudulent, right? You get there's a person who calls you, right? That event basically gets transferred to someone who will handle that event by calling the customer, right? So that's event streaming, right? Then we have something called change data capture. So again, this is a technique used in EDAs where we track and record the changes made to data in order to create replicas for various downstream systems, right? So imagine a database and there are changes which are happening to the database. As and when those changes are happening, we are going to capture those changes and apply those changes to another clone that we have, right? So example, which is the example that I'm going to particularly talk about is digital decoupling, fast replicas for optimized reads, right? So this is a very interesting example that I'll talk about where change data capture is used. Okay, and then the last thing that I'm going to talk about is the CQRS, which is command query response aggregation, right? So this pattern is all about separating the read and update operations, right? So typically, you'll see that the there are certain systems where the number of reads are way higher than the number of writes. Okay, so those systems basically have to be designed for read optimization, right? So it should be more responsive to reads. That it will be written once and read many times, right? For example, orders, right? You will place an order once, but then at least 10 to 15 times you'll see the state of your order, right? Where it is, right? So it's basically the system needs to be optimized for reads and not just for writes. So in such cases, right, you develop a system where you segregate the responsibility of reads and writes, okay, through this pattern called CQRS, command query response segregation. But at the same time, you need to maintain a sync or maintain an integrity between these two data stores, right? And that's where you use event queues. So example could be, e-commerce applications where you have two data stores, right? Where one data store, which is meant for all the write operations, such as creating and updating orders. And the second database, which is dedicated to handling read operations, such as querying for order details and order history, right? So that's CQRS, command query response aggregation. The key element in this is an event queue, which will maintain the integrity, right? So these are the principles that I have found useful when I have seen practical implementations of event-driven architectures, right? Now, over the next 15 minutes, I'm going to walk you through certain, real-life case studies. I'm going to essentially walk you through 3 case studies on EDAs, and where I have used all of these, right? Now, let's, and by the way, all of these elements mentioned above are used in domain-driven designs and microservices-based applications, which, Mr. Degvikar also talked about, right? So let us look at some of these case studies. So my first encounter with events and EDAs was in 2012, when I was working for Oracle, and this term also may not be formally present, this whole term about events and event-driven architectures, but we are somehow building something which eventually would be called as an event-driven system or an event-driven architecture. So let me talk about it, right? So while in Oracle, I was working on this product called Oracle Enterprise Manager. So it's a software which manages, or it's a software which basically manages the data center, right? The whole notion of public cloud was still in the making, at least on Oracle, right? While the competitors had moved ahead, but the likes of Oracles and IBMs were not really into the public cloud space, right? So some of these systems basically were to be repurposed, as Oracle would launch their public cloud. And the most important system here was Oracle Enterprise Manager, which was used for provisioning software, monitoring, managing provisioning software, etc. Right? And the project that I was working on was cloud chargeback. So if this system, which is Oracle Enterprise Manager, kind of manages the data center, provisions stuff, right? There has to be a metering, there has to be a showback and a chargeback, right? So that's where it all started, right? Now, in this project, there are key moments of truth, right? And these were new discoveries which we were realizing, because the kind of problem that we were solving was totally different. And obviously we were expected to see a lot of surprises and learnings, right? So I'm going to talk about those now. So what are those moments of truth, right? So the first moment of truth was that the speed at which events are generated and the speed at which we can capture, store, and handle the event is not the same, right? Because we were kind of repurposing this Oracle Enterprise Manager to be used for a public cloud kind of implementation, right? So the amount of provisioning that will happen through this software, the amount of metrics that will come in, the kind of monitoring and the kind of events which will be generated in a public cloud infrastructure will be much, much higher than what we anticipated, right? And therefore, the speed at which these events are going to be generated and the speed at which we could capture, store, and handle these events were not the same, right? And therefore, the design that we had, the legacy design that we had for several years had to change, right? So that was the first moment of truth, right? And then the second moment of truth was that for these events, right, let me give an example of an event from the OEM perspective, right? So for example, a SOA suite provisioned, request being made for a SOA suite to be provisioned is an event, right? A CPU usage hitting its 90% mark, right, would be an event. Right? I talked about two different events, right? One event is very, very, the grain of event differs, right? We are talking about an event at a CPU level and we are talking about an event at a SOA suite provisioning level, right? So I think these events, there were multiple stakeholders who were interested in the same event, right? So CPU utilization going high, right, may be required for diagnostic purposes, may be required for metering purposes, may be required for chargeback purposes, because a chargeback is going to depend upon the usage, right? Metering and showback is an essential component anyways of the platform, right? So there are multiple stakeholders who are interested in the same event, right? And I mean, the earlier designs were such that everyone is handling the event in their own way, and therefore there are copies of the event being created, right? I mean, the term event didn't exist per se, but the data associated with that was sourced, stored, processed, separately by separate teams. So that was the second moment of truth, right? The third thing was, as we gradually move towards these event-driven architectures, without even knowing the term, such term exists, we started using events, etc. We realized that these events are generated at a much higher speed, and our ability to capture everything is not there, right? We are probably dropping some events on the floor, because we had started using Kafka. Kafka was in its stage of infancy at that time. It was not as mature that we have today, right? And therefore we had these issues of dropping events and not knowing what to do about it, right? So that was the third moment of truth, right? And the fourth one was, our ability to correlate events was not there. So what I mean by this is, if there are if there's something, something happens, right, to a SOA suite installation, maybe there is a configuration file which someone has changed, and because of that, 3 hours later, we start seeing some error logs, or we start seeing some performance issues, right? Now, can we correlate these two events, right? So for example, change in the configuration file is an event, and certain errors surfacing out or the performance degrading, can we correlate this, right? So at that point in time, there was no way for us to do this correlation, at least through Kafka and all, because Kafka, as I said, was in an infancy stage. Today, it has, streams, it has stream tables, you can join streams, right? So all of that, but it wasn't there back then. I'm talking about 2012, right? So this was my first encounter for events and event-driven architectures. But the key learning here was that the industry was moving from the traditional ways to capture events, to store events and process events. Okay, it was moving to a different system, right? By using things like Kafka. And in fact, Kafka also was like 4 to 5 years old when we started using it, right? It was invented in LinkedIn, and the problems that I called out, right, which Oracle was facing, similar problems are much more, at a bigger scale, perhaps LinkedIn was facing. And therefore, we had the system called Kafka, right? So that was my first experience of using this, right? Now, fast forward to 2015, right? Where I had moved out of Oracle, and I was with Accenture, and I was working for a global telecom major. And by that time, this term events, this event platforms, the need for events, was all everyone was talking about it, and everyone felt the need of doing it, right? And again, there I got an opportunity to build an events platform for a global telecom major. And there, the intent of building that platform was to support diagnostics and advanced analytics use case. Right now, typically in a in a telecom industry, right? There are two types of business domains, right? One is OSS and BSS. There are two types of systems rather, OSS and BSS, right? And there are things which actually need to be captured separately at an OSS level and a BSS level, right? So the intent there was to, first of all, look at events in that particular domain. So for example, the basic event that I can call about is a call data record, CDR. Right now, a call data record at a network level is different, and at a business level it is different, right? So at a network level, it will have a lot of details about the network device, etc., right? And it is not linked with the customer yet, right? It's about a call, which is not essentially linked with all the customer attributes, etc., but it's a call placed on the network, right? So capturing that CDR, right? And when it comes to a call, purely from a commercial perspective, from a customer perspective, right? It's a different event, right? So how do we build those scalable systems to store such events? Like CDR is just one of the events that I called out, but in real life in telecom, there'll be several such events, right? So we had to build this events platform where all these events basically will be stored along with their payloads, right? And I'll talk about this payloads. I think Mr. Degwekar also mentioned about the need to store events as well as payloads. Sometimes you store the events along with the payloads in a system like Kafka. If your payload is too huge, then that's not the right thing to do, right? Sometimes it is good to have your events stored in Kafka and the payload somewhere else, into a distributed storage, into an object storage, like an S3 today, right? So that is what. But back then, right? This system which was being developed was purely based on Kafka and Hadoop, right? SDFS, right? So again, there were some moments of truth, some learnings actually. In some cases, we realized that your payload, wasn't too big, but wasn't too small, right? And we wanted to save that payload somewhere else. And at that point in time, we had two options. Either you go and save the payload to a database, or save it to a scalable system like Hadoop or SDFS, right? And everyone was in favor of SDFS because that was the big thing, the new thing that time, right? We don't have to use expensive databases to store that, right? So let's store it into a file system and Hadoop file system. But only to realize that later that such systems are performant only for big data, big files, right? If you store smaller payloads into SDFS, right, that's not the best thing to do, right? So then we had to figure out what's the right thing to do there. But essentially the segregation of an event and the payload had to be done, right? So again, that was a moment of truth when we were implementing the system. And as we built the system, right, it became a unified system for monitoring the health of various subsystems, the KPIs, etc. And then finer use cases, right, were being developed on things which are related to advanced analytics, related to network planning and maintenance, or things which are related to customer churn, designing innovative plans and offers, etc. Right. So in this experience, the first thing was to build a POC, so to prove the point that yes, we can build event-driven systems by using Kafka and Hadoop, right? And then we started sourcing events from various systems, OSS and BSS systems, and they were actually landing now in the events platform, right? But again, this was very early stages. Basically even Kafka and Hadoop, they were growing actually, and no one knew at that point in time that this is a transition, right? It's not that these systems are going to live forever. We're in a transition phase where something more matured is going to come 10 years down the line, which we all know today, right? I mean, and no one would want to implement all of this on Hadoop, right? Or essentially just a Kafka, a homegrown Kafka cluster, right? Well, the principles remain the same, but the underlying systems were going to mature a lot, right? So, but it was a good start. So we could build that platform, events platform, where we started putting all the events there. And then once there was a confidence that these events, along with the payloads, are available, then various teams, started building their advanced analytics applications related to OSS or BSS, right? So that was the second, experience that I would like to call out here, right? And as I discussed in the previous slide, right, the four things that I discussed, right, which was about event sourcing, which was about event streaming, CQRS, right? All of that, I could see being used here in various shapes and forms, right? Now, let's talk about the third experience that I had, which was the most recent. Again, it is basically an Accenture, and then Accenture actually has a point of view and has a solution, an architectural approach for digital transformation, and we call it as digital decoupling, right? So this is all about unlocking value from legacy systems, right? So let me give you a specific example, right? So in the insurance domain, even today, right, the entire policy administration today is done on legacy systems, right? They are called as PS, policy administration systems, right? Those are legacy systems, and they while we call it as legacy, but those are the core systems actually, right? Typically, when we say that this is legacy, people think that it's of no use and soon going to be replaced with something else. But in the insurance domain, some of these systems are core systems and they will continue to be core systems. There cannot be a replacement to that, right? Now, they manage the complete policies lifecycle very well, right? But when the digital wave started, right, roughly 15 years ago, it was very difficult to build a digital layer on top of these systems, right? Because these are very closed systems, right? They do not have any APIs, right? They do not emit any data, they do not emit any events, right? So how do you break that, right? How do you enable these systems for the digital transformation, right? So that's all of, that thing is taken care by digital decoupling, right? As an architectural approach, right? So one of the important principles that we used there was about change data capture, right? So until now we have been talking about events in general, but actually events can be of two types, right? It could be technical events, it could be business events, right? So for example, technical event is easy to understand, right? So you make an insert into a database, right? It's an insert query, right? It's a technical event. You are going and changing the state of a table, right? You're changing the customer attribute, maybe, right? Your customer's address has changed, right? It's a technical event, right? But at the same time, there are some business events, right? For example, a policy is approaching maturity, right? And there is a trigger that, before the policy, approaches maturity, 90 days before that, I should get a trigger, right? And something I should be notified. It's a business event basically, right? So, or, aggregate of events, combination of couple of events, right? Could be a super event, right? So those are business events, right? So we have to develop this whole, change data capture system so that data and value can be unlocked from these, core systems or legacy systems, right? So the CDC technique is one of the important technique in EDAs in such cases. Then this technique also was to, build for fast replicas or clones. And as we all know, right, because of the digital layer that we have on all the businesses today, our ability to access data, right, and services has improved a lot, right? And therefore, the kind of reports that are generated, the kind of actions which users have are very high. So for example, you can just go and check the status of your policy or check the details of your policy, as many numbers as you want. Just you can do, kind of send an SMS to a number and you'll get the status of your policy, right? So these kind of queries, right, are typically referred as SOAs, system of account queries, right? So there was a huge rise in SOA, system of accounts kind of queries, right? And to handle those kind of workloads, you need to create, replicas, right? So while the policy administration happens in the core, right, but it emits data into fast replicas. So all the read loads basically, or the SOA type of requirements will be served through the fast replicas or clones, right? So that is another aspect of digital decoupling, and therefore applying digital transformation, right? And by doing this, right, by kind of identifying business events and technical events, and then basically emitting those events out of the core, right, through change data capture, and then emitting it a way that the downstream applications can bring in those new digital experiences, right? So that was about digital decoupling. Yeah. But overall, EDAs basically has, have evolved over a period of time. At least when I started working on it, I don't even remember whether the term was formally there, right? No one in Oracle there back then told me about this term EDA or events, right? Perhaps we naturally, started working in that direction. And the reason for us to move there was, as I said, right, we had this Oracle Enterprise Manager, which was managing a private cloud, right? And it was to be repurposed to manage a public cloud. And therefore, we realized that we had these moments of truth. We realized that the existing design and architecture will not work. So there has to be something different. And that's where it all started, right? It's been around 12 to 13 years now. I have used it, on various occasions, and have seen it in being implemented in various projects. I would say, this is a wonderful architecture which scales very well, right? And it is one of the important levers to enable digital transformation, right? So with this, I'll take a break here, and I'll hand it over back to Mr. Degwekar.
Well, thanks a lot, Mr.
Thank-
Rahul. So let's get into some Q&A, right?
Yeah.
Thank you, Anil. Thank you, Rahul. Would request the participants to kindly ask questions. It can be through chat or through voice.
Vikash here. Thank you for such a great um, session. You'd like to understand, like you have mentioned about once the data
sorry.
goes. Yeah.
Can you please introduce yourself, saying which organization you're part of, and then ask question? Yeah, thanks.
Yeah, I'm from Happiest Minds.
Okay.
Vikas Kumar from Happiest Minds. So in one of the use cases, you have explained that there were a lot of data or the topics were created, and to correlate the data, it was getting a problem. So how do we solve that kind of issue? And the second question is, if there is any sort of a transaction that we have to maintain with the event-driven architecture, then how that would be possible?
Rahul, you want to take that, or?
Yeah. I'll talk about the correlation part, right? So let me give an example of the correlation part, right? Which didn't exist back then when we started using it, right? Consider example of Ola or Uber, right? There are two streams you can consider. I mean, basically how Ola works, basically, right? It is basically a bunch of people who are searching for cabs, and there are a bunch of cab drivers who are searching for a passenger, who can take a ride on their cab, correct? So how do we marry these two, right? We marry these two streams basically, right, to find the correct match. So there is a set of people who are searching for a cab, and there are cabs who are available waiting, searching for a potential client, right? So these two streams basically can be married through a join, like a typical join that you do in a database, right? And you can actually do a matchmaking, right? Similarly, in event-driven architectures and even in Kafka today, right? You have the ability to create streaming tables and do joins in a window, right? So there is a stream of data which is coming. Let's call it a stream 1, and another stream 2, correct? And I need to join those two streams together for a period of 5 minutes and take necessary actions within that window of 5 minutes. I'm telling 5 minutes as a big window. It typically is not that big. It will be maybe 5 seconds or 10 seconds, right? So that's the correlation aspect of it. Like where we had to use correlation was there was a stream of metrics coming from various devices. I mean, not devices, but various targets. We have to call it the targets. These are target metrics. And how do we marry them, right? So for example, the performance of a SOA system, okay, has gone down. Is it because of a particular change configuration in a file, right? So how do I marry these two streams and tell that, look, this particular event, which is change in the configuration file, is going to lead to the other event, which is indicating that the SOA system has slowed down, right? Or vice versa, right? The answer there is that, we join these two systems today, two streams today to be able to correlate. Yeah. And the second question was about, do we have, I think your second question was about transactions, right?
Right.
Yeah. So I think as we fast forward, right, in the last 10 to 15 years, I think there was no transaction support. There was no formats specifically for these things. So now we come to environments like Databricks, where we have this notion of Delta Lake, right? So all these events basically can be stored as Delta Lakes with transaction support, right? So it's not that your event is immutable, right? I mean, you can still, maintain the history and, edit those by ensuring that you have ACID compliance.
Okay, thank you.
Any other question?
Netaji here, please share this recording so that it will be easy for us to go through this once again.
Yes, the recording will be uploaded and the link will be shared. Any other questions?
Hi, this is Pradeep from Happiest Minds. So the question which I have is, do we have the ability to perform set of transformations or perform aggregations on top of the data which is event driven?
Yes. With windowed operations, right? You can do that, I mean, Apache Kafka, Confluent, or the equivalent systems on the cloud, right, allow you to capture those events, aggregate them, transform and aggregate. It's called in-flight processing, right, and aggregation. So there are abilities to do that in the modern systems today.
Okay, thanks.
Hi, this is Sharik here from Dell. I have a question. Like, you had asked to use open source kind of products for event-driven architecture. I have a specific use case for MQTT based for IoT applications. So is this still applicable? We should use open source, or we should go to MQTT specific products like EMQX, HiveMQ, then going to RabbitMQ kind of a stuff?
No, I think I'm sure, open source will always work. There will be open source solutions available. I mean, you can, in general, we'll look for open source solutions for two reasons. One is portability across cloud. Other is, you reduce license cost, but, it's an evaluation you need to make, right? I don't think a specific answer can be given at any point in time. It's a trade-off, obviously.
Thank you.
Okay, so I mean, if there are no more questions, then I would like to thank everyone for their attendance. Anirudh, you want to say something?
I wanted to take over. Thanks a lot. Firstly, thanks everyone who've attended the webinar, who've taken time out of the busy schedule. And I want to extend a special thanks to both Anil and Rahul, who out of their more tight schedules have been able to take time out, share insights with us. Thank you very much for the great session. Thank you, Anil. Thank you, Rahul. And we'll be shortly sharing a thank you mailer with the details of the recording.
Okay.
Thank you, Anirudh. Thank you, Stackroot team.
Thank you, Rahul.
Thank
Thank you,
you.
Anil.
Thank you, Rahul. Thank you, Anil.
Thank you, Mr. Anil. Thank you. Bye.
Thank you,
Bye.
Anil. Thank you,
Bye.
Rahul.
Bye.